So, hello everyone. So we are going on the next session, which is dealing about material processes and chain opératoire, the second part. I'm Niels Blanc from the Institut Néel and the Beamline BM2, French CRG at the ISRF. And I'm pleased to welcome Victor Gonzalez from the Research Museum. And you have 14 minutes.
Thank you, Niels, for the introduction. I want to start by thanking warmly the organizers for inviting me. It is very nice to be here at the ESRF because I do remember that my first beam time ever was here on ID 22, I think. So yeah, it feels really nice to be here with my community. And today we are back to structural studies that Koen Janssen already discussed yesterday, but I'm going to present to you some other cases which you might find interesting. So, today I'm going to try to convince you that synchrotron radiation and most specifically structural studies using synchrotron radiation can bring us some answers to questions that we have when we are dealing with historical paintings and most specifically inorganic pigments. And to do that, I'm going to showcase a few examples which will have to do with the materials and techniques of Leonardo da Vinci, the creative processes at stake in the work of Rembrandt, and finally I'm going to briefly discuss the in situ formation of crystalline compounds in oil paintings. And at the end of my presentation, I will present to you a few open questions for us as a community to see, perhaps to reflect together on what the EBS will mean for us and what we will be able to achieve in the future. So, as a very brief introduction, but this was already presented this morning and yesterday, historical paintings are very complex objects. The reason for that is that the materials which compose them are quite unknown to us. So for example, if we are dealing with a pigment and we want to know how it was prepared in the past, yeah. Okay, so when we are dealing with this type of recipes, you can imagine very easily that it's difficult to understand. And when we do have some insights on how the pigments were prepared in the past, well, we quickly realize that those synthesis processes are very complex. So in the case of lead white, for example, Koen yesterday already discussed this pigment, and I'm going to talk a great deal about it today again. We know that lead white was obtained by placing metallic lead in the presence of acetic acid in jars, and those jars were covered up in horse manure for several months. And this induced the corrosion of the lead, and then the powder was collected, post-prepared with some post-synthesis processes, and finally we obtain the pigments. So we might think we know something about this pigment, but actually when we look chemically in detail what is going on at the various steps of this process, it's actually very complicated. For example, the corrosion process for lead white involves a lot of intermediate crystalline phases and so on. So elaborate ancient synthesis with unknown parameters. The second order of difficulty when we are dealing with inorganic pigments and historical paintings, and this was presented again this morning, is that those paintings are very dynamic objects. So Friederike this morning presented you this exact same example of these yellow roses, and to convince you that something happened here, well, this is the chemical imaging of arsenic, so you can see that this flower, which was so delicately painted in the past, now has lost a part of its beauty. So, again, dynamic materials undergoing chemical changes at the micro scale. So to try to overcome these difficulties, what we are used to do is to go to synchrotron facilities, and to do that, this was already told again, we are used to collect microsamples carefully at the surface of paintings and bring those samples at the synchrotron, where we will rely on the state-of-the-art analytical capacities in order to perform some very advanced characterization. And in my case, I will deal mostly with the structural study. So, what does it mean, structural study for me? I'm going to look specifically at several parameters which I find are of interest when trying to understand the materials I'm dealing with. So in the case of lead white, for example, 3 specific parameters are very interesting to me. we know that lead white is composed of two lead carbonate phases, cerussite and hydrocerussite. Well, using synchrotron radiation, I will try to access a precise quantification of those two phases, perhaps access their distribution at the microscale, or they are placed next to another in a complex paint stratigraphy. And finally, I will try also to access the crystallite sizes, because this also is a clue on how the pigment was prepared and evolved. So let's start with some example regarding Leonardo da Vinci. So we are going to focus specifically on his use of the lead white pigment. So as I told you, we know that the lead white pigment in the times of Leonardo was prepared through this corrosion process. But actually what we are very interested in is those post-synthesis process. We know that it was very unusual for painters to use the raw material directly in their painting. We know that they were using several post-synthesis processes before accessing, let's say, a pure pigment or a pigment which was considered as beautiful to paint with. And what we think is that those post-synthesis processes actually have an effect on the structural nature of the paint. So this paint, which was post-processed, has a specific structural signature. Our research convinced us that actually when you obtain a raw lead white pigment, it is most of the time in a classic, what I would call the classic ratio of hydrocerussite, cerussite greater than 60:40. So usually a pigment which was obtained through the classic way of synthesis is richer in hydrocerussite. But what we know is that in Leonardo's time, several post-synthesis processes were used in order to make the pigment more, let's say, suitable to paint with. One of those post-synthesis process consisted in washing or grinding the pigment in acidic environment. While by reconstructing this post-synthesis in the lab, we were able to see that actually because those lead carbonate phases are balanced through a pH-dependent equilibrium, washing in vinegar will induce an increase of the cerussite, which is stable at lower pH. Also, the dissolution and recrystallization will induce a decrease of the size of crystallite. On the opposite, another historical processes that we know of consisted in washing the pigment in aqueous environment. And in this case, we have the opposite effect, meaning that the amount of hydrocerussite will go up and the size of crystallite will increase. So basically, in the case of Leonardo, we were lucky to find some indication that indeed he used different subtypes of lead white. We know from a manuscript that he paid a certain amount of money for one lead white and an amount which was greater for another lead white. So most definitely, he used different grades of lead white. The question for us will be, well, can we find those different qualities of lead white in his paintings? So, of course, it's not the workshop of Leonardo, but we can imagine that things went quite similarly in his workshop. The master is here working, but what we are interested in is the work of those two apprentices. They are preparing the pigment using specific recipes, and we want to try to decipher those recipes and perhaps finding them again within the artworks. So to do that, the first step when we were working on lead white pigments consisted in going to the ID22 beamline at the ESRF to perform high-angle resolution X-ray diffraction. So in this particular case, this is a powder diffraction beamline. So the trick was to place our microsamples in glass capillaries. This is kind of tricky, but it works. And then we are going to actually irradiate those samples at quite high energy because we are working in transmission. We are probing the entire bulk of the sample, so you have to be extra careful in having a sample which has only one layer of lead white because the contribution of all your lead white will be mixed. And then we are working in transmission, meaning that the detectors are somewhere around here. And using high-angular X-ray diffraction, we are able to have some very, very high-quality data sets of structural information. And again, I'm interested in the quantification of my phases and the size of crystallite. We did that for a lot of samples of lead white. And if we plot the ratio of hydrocerussite on cerussite versus the size of crystallite, we can see that some groups are appearing. So I won't get into too much detail, but basically we can think that, for example, some samples which are characterized by a low amount of cerussite and a small crystallite size might be connected to a post-synthesis treatment in acidic environment. So the game then will be to try to think where Leonardo's sample fit in those groups. The main idea is that structural analysis can provide some information on the preparation recipes of historical pigments. So I'm going to present, to showcase an example which is even more precise in the case of Leonardo. So when we were reading Leonardo's manuscript, we were very surprised to find a very nice story that Leonardo actually had the insight of Rayleigh diffusion, or Rayleigh scattering in the past, because indeed he postulates that the blue color of the sky is not its intrinsic color, but is caused by, small insensible atoms on which the solar ray falls, rendering them luminous, which is quite correct actually. But Leonardo goes a step further, and to convince us of that, he says if you want to be convinced, you can use ceruse, this is lead white, take it and a very fine and well-grinded ceruse, and it will have a beautiful blue. And this is actually true. If you take some lead white composed of nanometric crystallites, it will have a blue hue. This is particularly visible here. We reconstructed this in the lab, so we synthesized the lead white with nanometric crystallites, and you can see indeed that this white has a very beautiful blue hue. On the opposite, if you have a lead white with big particles, well, it's very covering. This is basically a very white pigment. So what was interesting is that all the ground layers of Leonardo da Vinci, so the layers which he used to prepare his painting before going to his composition, all of those ground layers were characterized by a high amount of cerussite and a very big size of crystallites. And we think that it's actually, let's say, something which was well thought of, because when you use this type of big particles, they will recline under the brush and you will obtain a paint layer with an optimal covering power. All of those paint layers have big crystallites, are composed with an amount of hydrocerussite which is very high. We can perhaps propose that they were obtained through a post-synthesis treatments consisting in heating in aqueous environment. But when we go to this specific painting by Leonardo da Vinci, we had access to an exceptional sample which is located here in the mountains in a place which is very bluish white. So it's a place of the location of the painting where Leonardo was interested in having perhaps some kind of this blue white pigment. And indeed, it was very convincing that this top layer had just a few blue particles, but was composed of nanometric crystallites. What's more, we found that this lead white is indeed composed of something rich in cerussite. So this is kind of something that Kuhn presented yesterday. We have here a lead white paint which is rich in cerussite with nanometric crystallites. So we thought, oh, maybe this has to do with some kind of post-synthesis treatment in acidic environments. But we wanted to confirm that, go a step further. And to do that, we were interested in looking at very precisely the microstructure or the peak shape of our pigments. Indeed, something we noticed, and which is absolutely impossible to do if you don't have access to very high quality data sets, so very high angular resolution like at ID22, is that a lead white obtained through corrosion is, let's say, characterized by what I will call a good crystallinity. So when you obtain lead white through a slow corrosion, your diffraction peak, this is a zoom on 2 peaks of cerussite, will be nice and symmetric. But if you induce some fast crystallization, you will obtain what is called crystal twinning. So in this case, you have asymmetrical Lorentzian broadening, and you can see that your peak on the left here and on the right, they are starting to broaden. This is actually a natural crystal, and this is something that we obtained in the lab when we made sure to induce some fast recrystallization. Well, sure enough, what was very interesting to us is that the cerussite of Leonardo did show this broadening of peaks. And so to us, this might mean that indeed, this is a clue that this specific lead white rich in cerussite with nanometric crystallites and with this broadening might be indeed obtained through this post-synthesis. So you can see here how synchrotron radiation can allow us to go a step further and try to have very precise clues on how the pigments were obtained in the past. Now, I'm going to showcase another example, and this is some work which was performed over the course of the last year, 2 years at the Rijksmuseum Science Department. We were interested in Rembrandt impasto. So for those of you who don't know what impasto is, it's this very thick paint. If you've been in front of a Rembrandt painting, you can, if you go close enough, you will see that the paint actually stands out of the canvas. It's really a tri-dimensional aspect. We knew that Rembrandt impasto was based on lead white, so this mixture again of hydrocerussite and cerussite, but the precise recipe was unknown. So our idea was again, let's take some cross-section from impasto area and non-impasto area and see if we have some specific structural features. So again, back to ID 22, well, the first thing that we observed is that in all of the impasto samples that we had, a mysterious phase was showing up. Plomonacrite, this is another type of lead carbonate, but much less common than hydrocerussite and cerussite. It was detected before by Kuhn Jansson's team in Van Gogh painting, but it was linked to the degradation of orange pigments. So in our case, it was very interesting to see that all impasto layers seems to be characterized by this presence and in high amount of this plomonacrite, which was linked to impasto. As usual, we also wanted to have information on the microstructure of this phase. And what was interesting is that within the classic lead-white matrix, well, our crystallites of plomonacrite were of nanometric sizes. So we had this nanocrystallites of plomonacrite within a lead-white matrix of greater size. Okay, so the idea after that was, let's see if Synchrotron can help us see where those specific phases organize themselves within the paint stratigraphy. So to do that, we switched to another mode of synchrotron analysis. This is structural mapping, and it was presented to you several times already. So the idea is simple. You have your microsample, and you will translate it in front of the beam in order to map a larger area. So what you will do is translate your sample. The sample is actually moving. And in the end, what you obtain is a map of the distribution of your phases. We did that at the ID 13 beamline at the ESRF. So you can see here, the sample is here, the beam comes like that, and we have our translation. This is a detector. In this case, we were working at 13 kiloelectron volt. So we need to work on thin section because the amount of matter that we will go through has to be minimal in order not to have too much shadowing. So this is something that Marine is renowned for, is the preparation of thin section. The idea is that we will cut a piece, a very thin piece of the cross section in order to have a very limited amount of matter so the X-rays can go through. Okay, so what we were lucky to have is a very nice sample from the Louvre where we had one layer of impasto, this white layer, directly on top of a white layer, but which is not impasto. And what was, again, very convincing is that this plomonacrite phase was localized only in this impasto layer. The classic lead-white layer, which was used for the ground, was composed of hydrocerussite and cerussite, as you would expect. So it did seem, indeed, that plomonacrite is linked to impasto. And in other samples, so this is just a chip of pure impasto, I would say, we can see that this, in red here, the plomonacrite, is homogeneously distributed within the entire bulk of the impasto. So this is not something which is, for example, a surfacic phenomenon, like Laetitia showed this morning, where you can see this phase only present at the surface, which we might think then, it's a degradation process coming from the atmosphere. It seems that plomonacrite has appeared in the entire bulk of the sample. Okay, so we had a lot of clues, basically, this homogeneous distribution of plomonacrite in the form of nanometric crystal. So we thought, well, maybe this is connected to the in-situ formation within the impasto layer. And now the question that we had, well, can we retrieve the chemical pathways of this formation? The main clue that we had is that plomonacrite is a metastable phase only existing at a pH greater than 10. So it's only stable in alkaline conditions. So from this, we were able to say, well, perhaps an hypothesis would be that Rembrandt used some litharge-based oil. We know that this type of oil was mentioned in historical sources, so it was not, let's say it's entirely possible that Rembrandt did use this type of oil. We know that a litharge-based oil has interesting drying and rheological properties, which might be interesting to build this very thick paint. So our hypothesis was, well, perhaps a mixture of lead white in the presence of litharge might induce the formation of plomonacrite. So to, let's say, confirm this hypothesis, we went back to the lab, prepared a lot of model. The internship of Tiffany Tang was done at the Rijksmuseum Science Department. And indeed, going back to synchrotron mapping, we were able to see that at the microscale, this is an undissolved litharge particle in an oil matrix. You can see indeed this nice ring of plumonicrite starting to crystallize around the lead arch. So this is just a first step, but we think that the origin of plumonicrite can indeed be linked to the presence of lead oxide within the oil. Just, it could interest you, you have until the 16th February to visit this very nice exhibition in Amsterdam, where this work was showcased, and actually you can see here, the ESRF is present. So if you are in Amsterdam, you can see this nice exhibition where this work was showcased and a lot of other complementary works done at the Rijksmuseum Science Department. Okay, so very briefly, before my conclusion, I'm going to present just a few results regarding the in situ formation of mineral compounds in oil paintings, because this is something we are very interested in at the Rijksmuseum. As I told you, paintings are dynamic systems, and in this case, we are not really interested anymore in how they prepared the materials, but rather how the materials evolve over time. So they don't have control anymore on that, but today, in 2020, we can have an insight on how those materials have changed. So, for example, this is some work which was done with Katrin Koine on the presence of lead sulfate in historical paintings. Koen also showed some results regarding the specific crystalline materials. Well, in this type of paintings where we observe some very strong degradation, we were able, through structural mapping, to map the presence of those lead sulfate, either palmerite close to the surface or anglesite close at the interface between a ground layer of gypsum and a top layer. So for us, actually, what is very interesting and what is mandatory to understand is the origin of the ions which are necessary to form those non-original products. And in this case, for example, well, the lead is quite easily connected to the presence of lead white in the stratigraphy. But for example, the sulfur ion, we have several hypotheses that could come from the atmospheric SO2, so let's say pollution from the atmosphere, but also from the presence of gypsum. And what is interesting to us as well is that structural mapping at the synchrotron can allow us to see that those type of compounds don't always crystallize under the same, with the same aspect. So you can see here that in this painting, we obtain some thin layers of non-original materials, but on other paintings, they actually have a very different shapes. So we can see here in this painting where we had those protrusions, those big lumps of non-original materials protruding to the surface. You can see that palmerite here is not a thin layer, but it's actually this very big, let's say, lump within the lead white matrix. And in this particular case, we think that this aspect, this way of crystallizing, can be connected to perhaps conservation treatments. So the main idea is that the distribution of those in situ formed compounds is critical to understand their origin. And actually, as Koen mentioned yesterday, we are right now involved in a very big conservation and research project on Rembrandt Night Watch. We are doing that in front of the public. And the presence of those non-original compounds is something we are very, very interested in the Night Watch. And I'm sure that when the ESRF EBS will start again, we will have plenty of interesting samples to bring at some point. Now, still on the in situ, I'm going to very, very briefly give you, this was already discussed through a poster clip, but this is a new project which involves several institutions, and it has to do with the presence of lead phosphate compound. So with Marine, as we were looking at the samples from Da Vinci again, we were surprised to detect this very thin layer containing phosphate. And actually, Synchrotron Micro-XFR confirmed that this layer was composed of phosphoediphane. What was interesting is that at the same time, Marine was working on Egyptian papyri, and in this papyri again, she detected the same phase. There is a poster, number 14, where you can read more about this study. And so basically we have questions, because those lead phosphate, we don't know if they are original product, if they are degradation based. And what's very surprising is to find them at such a different, let's say, historical time and geographical. So the main question is explained in this poster, and all of these institutions are now collaborating on this new project on lead phosphate phases. Okay, so through this presentation, I hope I convinced you that synchrotron structural analysis can reveal the old masters' lost recipes, but also shine light on the evolution of their materials. So the question for us now as a community is, what about the future here at the ESRF EBS? So I'm going to present to you a few questions that we can maybe all reflect on together and try to think if we can maybe have some new directions to go as a community, not limited to paint studies, but when we can have access to this new instrument. So as a first example, something which will definitely change are the acquisition time. So I remember when we first came to ID22 in October 2014, we had to switch the sample every 2 hours. Now at ID22, you have robotic switch of pre-prepared sample, which means that you can go to sleep. It's very nice. You can prepare all your samples, and then they will be all analyzed as follows. But, for example, in the case of crystalline mapping, this is something that changed as well. When we were with Marine in May, so only 2 years ago, this was 1 night of analysis, and this was already particularly fast at the time, meaning that in 1 night we could map 15 samples or so. With the ESRF EBS, technically, we would reach such speed that in 1 night we could theoretically achieve more than 300 samples analyzed, which is ridiculous, because basically this is more than any usual corpus analyzed during a beam time. And the question that we should ask ourselves is, should we rethink our access modalities? Should we develop faster processing routes? Because this is something which obviously we'll have to change as well. And I'm pointing to this session on Friday afternoon, where the session Beyond Instruments and Data Collection, where I think we should discuss this type of questions. Something else is the question of new chemical probes. So in the past, we've been working with photoluminescence. This is something which was already showcased here during this workshop. And we showed that by exciting your lead white in the deep UV, you were able to perform some fast crystalline phase identification. Now, this was done in the lab. We know that at the ESRF, there is some, let's say, other chemical probes that we might be able to use. So, for example, Xiol, so optical luminescence excited by X-ray, is available. So the question that we should ask ourselves is, should we explore new probing techniques with this new ESRF EBS? But of course, then perhaps a theoretical approach is needed, because photoluminescence mechanisms are very complex. So the question maybe is, if we want to explore those new routes, do we want to go this direction? Okay, and finally, what I found the most interesting part for me is that the question is, can we get the best of 2 worlds? So basically, I'm used to work with high angular resolution on ID22, where you have obviously this state-of-the-art synchrotron data, but you have no mapping capacities, meaning that I map an entire sample. On the opposite, for example, on ID13, we have those excellent mapping capacities, and soon they will be extremely fast, but the angular resolution is quite low. So what you can do is perform some identification and charting of your different crystalline compounds, but that's about it. So let's say, as a dream, what would be amazing is that I can combine this mapping of my sample, but I can, let's say, selectively say, well, in this paint layer, can I have access on the microstructure of my sample? On this paint layer, can I modelize these particles of pigment? And there is this talk by Catherine, which is Beamline's post-ESRF upgrade phase, where perhaps we should discuss this idea of combining the high angular domain with the high lateral domain. So that's about it. I want to thank all of those people. I'm not going to list them all, but this work is obviously very collaborative and a lot of people are involved. And I want to finish by perhaps advertising for 2 meetings I'm co-organizing. The first will be held at the Rijksmuseum Science Department, and it's a workshop on the chemistry of lead in oil painting. So perhaps you realize now that lead is basically kind of omnipresent in oil paints, and this will be discussed here with a lot of excellent speakers, such as Koen Janssen, Reinkot, Laetitia Monico, always the same. And we have 7 spots remaining, so hurry up. And the other meeting I'm co-organizing is the Gordon Research Seminar on Cultural Heritage Research. This will take place in Switzerland in July during 2 days. And this meeting is only dedicated to young research scientists. So young research scientists are PhD, postdocs. Basically, if you have a permanent contract, you're too old and we don't want you. But that's okay, because you can then join the Gordon Research Conference, which is organized by Loïc, who is here today. and which will be directly after the workshop. And here, all people can still submit abstract, Loic told me. So you can also discuss with Loic if you have any questions, and with me about those conferences. Thank you for your attention.
So we have time for questions.
So the association of the plumbonecrite to the impasto paint. So as you explained, this is through this oil, or could be through this oil.
Could be.
So I wonder whether the oil was then also used for non-impasto paint.
Sorry, you mean is there?
Yeah, is the connection exclusive to the impasto paint, or could the litage-rich oil also have been used by much more refinedly operating painters? That's what I'm wondering about.
That's absolutely indeed. This is a working hypothesis, but indeed, for example, in the case of impasto, there is now a new project being developed at the Rijksmuseum where it will be more focused on, for example, the morphologies of crystallites, and if this has something to do with the rheology. So there are different routes of to approach this painting, this problem. Sorry, we basically the fact that plumbonecrite is present means that something is alkaline. So to us, this was the most obvious answer. This litarge-based oil, but it's and I should say also that we have performed some other beam time, for example, at Diamond and I-18, where we have worked on a lot of model samples where it seems to fit with plumbonecrite crystallizes when litarge is present. But then, of course, is it only something due to the oil? It's, yeah, we still have a lot of work to do on this specific phase, and I know that your team detected plumbonecrite in obviously non-impasto layers because they are coming from other paintings, other painters. So this is perhaps not the only chemical pathway to plumbonecrite.
Some other questions?
Oh, it may be that in the samples where you detected plumbonecrite, it also comes from lead oxide.
Yeah.
But basically, our hypothesis is that when we found plumbonecrite, it means that lead oxide was probably used, and probably at such an extent, or with particles so big that it remained available for reaction with CO2 and water to form plumbonecrite, even if there are probably many cases where litarge was used, but completely reacted with oil to form lead soaps. So it may be a trace of remaining not for so long, because plumbonecrite forms in 1 month.
Fast,
yeah, very fast after the preparation of oil.
Yeah, a few hours.
One might ask the question of how the litharge was produced and whether it was a uniform phase. In Chinese art of the Song and Ming periods, we see litharge in coarse grains which has the consistency of a shell of lead oxide around a core of lead carbonate, and it affects the appearance. It gives it a brighter color. Depending on the way that the litharge was produced, in that case probably by roasting incompletely.
Yeah.
One might wonder whether the litharge used was really pure litharge.
Absolutely. So obviously the experiments we did in the lab was with pure litharge, but we do think that a key parameter is if the litharge is entirely dissolved in the oil or not. So according to us, well, so far it seems that the experiments are showing that you need to have some, let's say, still a remaining grain of litharge for this crystallization to kick in and start from this litharge. So indeed, perhaps the preparation method of the litharge could be connected to the dissolving capacities of the litharge in the oil and could be indeed linked to this specific chemical pathway. So this is indeed something very interesting to follow on.
And also related to that, lead oxide can be present as litharge and massico.
Yes.
And for example, in some text of Leonardo da Vinci, he mentions massico So both may have been used and probably used as a mixture. Quite probably.
Yes, most probably.
If I may, just if you can come back to the slide where you explain the preparation of scene sections, since this is my favorite subject, just to make it clear, because the explanation which is given is in a particular case where the cross sections had been prepared maybe decades ago, and they were coming from a collection of cross sections. So it just to explain this particular case where we wanted to prepare scene sections, but years after the preparation of the original cross section. So the cross sections that you see on the left was from a database collection of samples, and we wanted to extract scene section from this. And instead of cutting parallel to the surface of the sample, what you see here is that we decided to cut perpendicular to one side of the section. So meaning that even if you have samples which have been sampled, taken decades ago, embedded decades ago, and you consider that scene sections may be better than cross sections, is something we can do a posteriori, just to explain it. What I like in making scene sections is that you have a very good control of the volume which is analyzed. And in particular, when you do mapping in transmission with micro-X-ray diffraction, you know exactly the volume which is probed, and you have a good chance that the composition is homogeneous in the beam direction. So this is my advice.
So if there's no more questions, we can thank you again, Victor. Now, Emilie Chalmin from the Université Savoie and Editem Laboratory will present us shed light on the schematics painting of Savoie, the use of Micro-XFR to understand the painting walls.
Thank you for the introduction. Okay. I'm happy to be here to present you our research. No, it's okay. On the schematic painting of Savoie, so in France. So in the frame of the project called Patrimalp, we are 7 laboratories coming from the University Grenoble-Alpes and the University Savoie-Mont-Blanc. And we try to develop the study on cultural heritage. And we want to also create a consortium to develop this study on different objects coming from a geographical environment specific to the Rhône-Alpes region. And this object cross the time from the prehistory to the Middle Age. And among these different objects we studied during this project Patrimalp, I want to focus today on the schematic painting and more specifically the site named Rocher du Château. And I want to explain how the use of the Synchrotron X-ray enabled to perform and to increase the data on these paints. So these schematic rock paintings are present different shape, different figure, and there is a large thematic we can find. More specifically, we can found some engraves, but also some paintings, mainly created with mineral pigments and hematite pigment or natural pigments. That means that we can't do any absolute dating on this paint, and due to the archaeological environment and the repartition and the corpus of this schematic painting known from the Iberian Peninsula to the Western Alps and at the frontier of Italy, they can attribute, archaeologists can attribute this schematic painting to the Neolithic period from the 5 to 2 millennia before present. So this corpus presents 1,036 sites, and obviously it's difficult to study all of these sites, and only one archaeologist tried to understand this corpus about the schematic paintings. She's Claudia Dufran, and we try to help us to study with an integrative approach to know more about these schematic paintings. And to do that, we try to develop this integrative approach based on archaeological approach, geomorphological approach, and physicochemistry of the painting matter. So this integrative approach try to answer to different questions about the context and the environment of this realization of this paint, when, and the question of the chronology and the attribution to the period and to the because we can't have an access to absolute dating, we need to cross over a maximum of information to be able to create this chronology of this large corpus. So we also answer this question about alteration, conservation, and also we want to try to understand what is the supply strategy for the material, coloring material. So I want to focus more today on this physico-chemical approach, from the in situ observation to the analysis of the wall sample on archaeological artifacts. So first, we try with a digital camera and portative instruments such as Raman spectroscopy to study directly the paint in situ. But we need also to have an access to more detailed information inside the pigment, and to be able to understand the stratigraphy due to the complex stratigraphy, due to the crust and the byproduct mineralization. So we need to analyze at several scale, and we need also to take care of this archaeological artifact, and also from this tiny sample. So I will develop after the result obtained with different method on this different sample. And we cross also with synchrotron X fluorescence and diffraction X-ray. And thanks to the collaboration with the SRF in the Patrimonial project, we have the access to two beamlines, T2AM and ID22, to be able to make mainly X-ray diffraction. So the difficulties is to keep the sample entire and to avoid any preparation. But so you have several examples before about these difficulties to keep it between two ultraline film, and also to keep entire also the archaeological object, even if it make a few millimeters or several centimeters. So about the Rocher du Château, the Rocher du Château is situated in the Haute-Maurienne in high altitude glacier valley, and this serpentine block is particularly impressive in the landscape, and is situated in the circulation axis, which has been used from the Neolithic period. So inside this Rocher du Château, the paints are developed on about 80 meter long at the bottom of the cliff of this huge block, and there are several excavation squares realized by Eric Thiraud at the beginning of the 2000s. And we try to understand the development and the different figures we can find in this Rocher du Château. So a large panel with a red deer with the oversized antler. It's painted in a concave area of the cliff, and also schematic figure composed of anchor-shaped figure. So I present here the relevé created by Claudia Defran, because if I present you the formal and the realistic picture, we don't see really the paint, because it's like a shadow. It's completely. It's really difficult to see and to be visible, this paint, and so the conservation is not it's not very good for this paint. In the archaeological layer, we can find several artifacts which enable to constrain and to understand the period of the settlement, and associated with pigmented matter attributed to the second half of the 5th millennium BC. You can see different various kind of matter, coloring matter, are more or less cohesive, and that means that we need to adapt also the analysis as a function of this sample, of this object. So the Rocher du Château is a site particularly important and interesting because of the exceptional coexistence of the schematic rock art and the date coloring matter. And we want to know if the comparison of the composition of the painting to the archaeological coloring matter from the archaeological layer could provide an argument in favor of the dating, and could be also an information about the strategy, the supply strategy, and also the preparation. So first, we need to start to understand the taphonomy, the very difficult crust, several kind of crusts. Here on this cartography at the large scale, we can see a large diversity of this taphonomy. And when we observe also directly in the paint, we can estimate the thickness of the painting, the strategy, and enable to find the best place to make sampling. We try also to make directly a Raman spectroscopy in situ, which reveals the presence of hematite, but also from this crust, the calcium oxalate. But we don't have any information about the stratigraphy and the high fluorescence effect due to organic compounds enable really to understand, and it's not systematic results obtained with the micro-Raman. So we need to go further and to try to understand this stratigraphy thanks to the analysis of microsamples. first by scanning electron microscopy, and which reveal the hematite embedded in the calcium oxalate and associated also with phosphate. And we focus with phosphate to be sure that it's coming from the environment, of if it's coming from the preparation, and as a marker, as a clue also of preparation. So to go further, we need to cross over every scale of observation at large scale and microscopic scale, and also thanks to the micro diffraction of X-ray, we confirm the presence of calcium oxalate, but also the presence of gypsum. And we find again the hematite with a very low crystallinity. About the coloring matter, a large variety also of morphology, and a large mixture of hematite with quartz, with also apatite. And we wonder about the origin of this coloring matter. And due to the morphology of the hematite, and also due to the elementary and the presence of some trace element, we suppose an origin from a vein mineralization. For the other objects, we are less coherent. We find directly by optical microscopy the presence of charcoal and apatite. That means that perhaps we have an access to origin of the mixture. And thanks to the PIXI analysis, we confirm the association between calcium and phosphate. We can link to the apatite. However, this apatite don't appear in the micro-X-ray diffraction. That means that it's not sufficiently crystallized to be detected by this technique. And we find also a very complex, very complex mixture in this. And we really have an importance to cross over at different scale and with different technique to be able to reconstruct the mixture of this sample, because the charcoal is not observed by micro-XRD and not by chemical observation. So I want really to focus on the complementary of the in situ and laboratory techniques and synchrotron facility. So it's really important to cross over at different scale and with the morphological, chemical and structural identification to be able to discriminate the pigment, the resolving byproducts, the sediment for the artifact, and the rock substrate for the pigment deposit on the substrate, and eventually the additional charge. So we find here various constituents for this artifact, and we try to understand the geological origin with the vein mineralization, but the presence of maghemite asks the question of an eventual heat treatment. And we need to go further thanks to transmission electron microscopy to be able to detect really and to answer to this question. And about the presence of charcoal and apatite, we can make the hypothesis of intentional addition. Concerning the painting matter and to be able to answer to the question, can make a link and a comparison between the painting matter and the artifact. The pigments are the same. The morphology are quite equivalent, but what is the clue to be able to say it's the same? It's really difficult to say it's the same. And we need to go really further, and we need to be very prudent to clearly pose this hypothesis and go deeper after evacuate the byproduct, the substrate. We we need to go and to understand more this amorphous phosphorus and to understand if it's due to lichen activity, to presence of apatite, and if it's coming from an additional intentional addition. I want to thank you for your attention.
So we have time for questions.
Thank you, Emilie, for this interesting talk. I have a question concerning the presence of charcoal in your sample. Maybe I didn't get it correctly. Do you think that the charcoal is coming from plant remains? Or is it only the fact that you detect carbon in your samples?
No. If you see, there is really charcoal coming from coming from the burning. Yes, it's not only due to the presence of carbon, but really visualize the shape and the morphology of the charcoal.
Okay. Because otherwise, because you have this combination between carbon and apatite, you can also think of burnt bone remains.
Yes, but we don't see any bones, and the apatite, it's not the size of the apatite. It's not sufficiently. So we see some crystal, natural crystal, but it seems there is 2 or 3 kind of different apatite inside the sample.
Yeah, but
due to the morphology, the color, and but any are crystalline.
Yeah, but in burnt bone, apatite is not necessarily crystallized.
No, I know.
Yeah. Okay.
Other questions? No, so we can thank you, Emilie, for this nice talk. And now we are. The next speaker is Maulliful from ILMI, Institute of Technology of London. And he will talk about burning before painting, art pigment from Karmin cave.
Check. Thank you so much for the opportunity for giving me, Maulliful Ilmi from the Bandung Institute of Technology, Indonesia, for presenting my project about the synchrotron radiation X-ray and micro-XFR based characterization of the rock art pigments from the Karmin cave, East Kalimantan, Indonesia. First, we're going to talk about the rock art. Rock art, as Dr. Emilie mentioned before, is a figures in the form of engravings, in the form of the paintings, and in the form of hand stencil. This is the illustration of rock art creation by spotting out the pigment from the mouth of the artist, prehistoric artists. The rock art motifs contains a civilization, anthropomorphics, or figure like human, and zoomorphic, animal-like figures, geometrics or schematics, and hand stencil. This one is the figures of rock art engravings from Sydney, Australia. And this one is rock art painting in the form of anthropomorphic figures from the Namibia. And this one is the hand stencil in the positive hand stencil and the negative hand stencil from the Patagonia, Argentina. Next, the rock art in Indonesia. Indonesia is one of the countries in South Asia with the many prehistoric rock art sites distributed around the island of Sumatra. We have the Harimau Cave in Sumatra. We have in Java, in Kalimantan, we have a Putu Sibau. We have Sangkulirang. We have Ketapang. And in Sulawesi, we have Kolonodale, Lindu, Maros Pangkep, and Muna. And we have also in Papua, we have some such rock art site in Papua, especially in Misal. This one is very characteristic. Recently reported that the oldest hand stencil dated to 39,000 years before present, and this one is the hand stencil figures, and this one is the figurative in the form of the zoomorphism, the oldest figurative rock art dated 40,000 years before present, and this one is the oldest hunting figurative in found in the Maros Pangkep in the South Sulawesi. We have it is dated 44,000 years before present. It has been reported by Aubert in 2014, 2018, and 2019 in Nature. About rock art research in Indonesia. Indonesia, we are a developing country, so the main focus of rock art research in Indonesia is still on the meaning and the religious aspect of rock art. But only 70% we are focusing on the chemical composition or the physical chemical studies of the rock art. However, actually, the physical chemical studies, we could have an information about the pigment composition, about the pigment provenance studies, about the indirect dating, about the pigment preparation techniques, and weathering potency of the rock art. One of rock art site or rock art region in Indonesia is Sangkulirang Mangkalihat region. The Sangkulirang Mangkalihat region is located in the East Kalimantan. This one is Kalimantan Island in Indonesia. It's located here, and this rock art region have entirely 15 caves contains rock art. One of the rock art on this site is dated 40,000 years old, the oldest in the world, as I mentioned before. Interestingly also, this rock art region contains a drawing technique evolution. This one is zoomorphic motif, painted with a reddish orange pigment, dated 40,000 years old. And this one is the hand stencil motif, dated to 20,000 years before present, in the Liang Tewet cave. And this one is anthropomorphism motif, the black pigment, painted with the black pigment, dated 4,000 years old. And it is correlated with the migration of Austronesia to Indonesia from the Formosa Island. This one is very unique because actually the purple pigment is commonly prepared by the heating of the red ochre. So in this era, the people or the prehistoric community already introduced fire for preparing the pigment, and this one is made by the charcoal. So they already introduced the burning or the charcoal from the burning process to paint the rock art. One of the rock art cave in Sangkulirang Mangkalihat is Karmin cave. The Karmin cave contains a very unique figurative. This one is figures, maybe is quite similar with the Tapirus indicus species, the extinct species in Malaya, or we call it Malayan tapir. It's already extinct 6,000 years before present. This one is painted by the dark red pigment, and this one is the beehives-like figures, which is very similar with the beehive tree in Kalimantan. This one, we could see this one. Maybe it is fading, but actually when we change and we zooming this picture, this one, we could have a figure something like this one, with the beehives. And this one is hand stencil figures painted with red pigments. So we're gonna analyze these different pigments, dark red pigment, the purple pigment, and the red pigments as object of our research. So the materials of the research is the 3 pigments sample with the purple, dark red, and red hues. This one is the sample of the purple pigment from the beehives-like figures, and this one is the dark red pigment from the tapir figure, and this one is the red pigments from the hand stencil figures. It is our samples under the microscope, the optical microscope, and this one is the Mansell color from the Perahu Institute in the Griffith University. We use it to categorize the color of the pigment. The challenge of the research are the small amount of the sample due to the archaeological consideration of the cultural object, and the sample in the powder form due to its low mechanical stability and highly fragile, and the sample has low content of the coloring minerals. The solution, so we apply the available synchrotron radiation based characterization in Southeast Asia. We have Synchrotron Light Research Institute in Thailand. Due to its high intensity beam in a broad spectral range, high collimation, and fast time measurement, it could provide a high resolution data and lower detection limit. So we do the several characterization. We do the X-ray powder diffraction characterization. We do X-ray micro-XFR fluorescence by using laboratory XRF, by using Orbis ADAX. And this one is the SANS by using fluorescence mode due to the lower concentration of the iron. This one is a result of the X-ray powder diffraction characterization from the purple pigment, from the dark red pigment, and the red pigment. This one, we could see that all of the pigment sample contains of gypsum, content of calcite, because the gypsum and calcite is minerals on the rock art, the rock wall in the karstic region. So this one also we could see wheelite. Wheelite is the byproduct of the reaction of the metabolism of the microorganism with the calcium minerals. And this one is a hematite. Hematite is commonly used to make a red pigments, something like this one. And we assume and we conclude that the hematite is a coloring agent of the materials of the pigment. And we do the SEM characterization to making sure the existence of the wavellite. So we could have the trait-like morphology, something like this one, that's supporting the wavellite finding, because the wavellite is coming from the reaction between the oxalic acid from the microorganism metabolism and the calcium minerals, calcite or calcium sulfate, and it forms the calcium oxalic or wavellite phase minerals. And then what is the difference in the hematite between the three types of a pigment? So we zoom the highest peak of the hematite, look at it here at a 22.1 degree. So we could have different properties of hematite. The peak of hematite and the purple pigment showed very strong compared to another pigment. So we could analyze by using the crystalline size, by using the Scherer formula. So we have the FWHM value of the purple pigment is higher compared to another pigment. Then the crystallinity on the purple pigment is higher than the dark red pigment and the red pigment. So the crystalline size of the purple pigment is larger than the dark red and red pigment. So we could conclude that the purple pigment, presumably obtained from the heating of the ochre in higher temperature, because in the crystalline minerals, so by using heating treatment or by using the annealing or a sintering process, we could have the more crystalline materials and we get a sharper peak. And then this one is Micro-XFR characterization. This one is the elemental composition pigment. We could see that the hematite on the purple pigment is higher than another pigment. And the characterization by using elemental mapping, by using Micro-XFR, we could see the irons is only located entirely the brownish part of the sample. The brownish part means the pigment, and the brighter one is the rock. So the iron is only located on the brownish part. So meaning that the characterization from the XRD, the hematite, is the coloring agent is true. It's already confirmed by the Micro-XFR characterization. And the last characterization, we use SANS. The SANS spectra is we obtained by using in the powder form. The SANS spectra we compared with the several standard, the FeO, the Fe iron hydroxide or goethite, and this one is a hematite. We could see that this spectra is quite similar with the hematite. And we do the analysis of inflection point, and we get the energy H position on the KH is located in the 7,126.6 eV, is indicated the iron 3 oxidation state. So actually, we do the linear combination fitting analysis also. The linear combination fitting is quite similar with the hematite. It's 100% contents of a hematite, not another iron 3 oxidation state species. And then we do the deconvolution of the pre-H scenes, FAKH peaks. This one is the result, and we have the different absorption phenomena of the three pigments. This one is the purple pigment with the higher absorption on the EG transition, and this one is quite low compared to the purple pigment, but it has a lower in the 3-2G transition. And so we could have the ratio of the peak intensity. So the purple pigment is lower than the dark red pigment and the red pigments. We assume that there is an octahedral distortion on the purple and dark in the purple pigment, higher than another pigments due to the heating process. The heating process could change the geometry of the coordination around the iron atoms. Around the Fe3 plus ions on the crystal, on the hematite crystal. We confirm this with the centroid plot of the pre-H peak. The result indicate the presence of the distortion of the purple pigment due to the octahedral coordination around the iron as a result of the different preparation techniques by burning the ochre at a different temperature. This kind of the hypothesis, or this kind of the assumption is already confirmed by Bora et al. 2012 in the case of the synthetic hematite. So we jump to the conclusion. The H pigment are consistent of a hematite originated from the red ochre. The purple pigment show the higher crystallinity than dark red and red pigment. The purple pigment has a higher hematite content than dark red and red pigment. The purple pigment has a higher, the purple pigment show the lower T2G compared to EG absorption ratio due to the higher octahedral coordination distortion of the iron as a result of the higher temperature burning pre-treatment. The different each pigment material was presumably caused by different temperature burning occurred during the pre-treatment. So this one is our schematic. So this one is the purple, this one is the dark red, this one is the red. So higher crystallinity and the higher thermal treatment. It is our hypothesis. So the further research, we are need to applying Micro-XFR characterization by obtaining suitable sample to get the deeper information about the crystal properties, especially about the cross section of the pigmenting materials, and the applying of microsense characterization to get a more representative result about the electronic structural differences between each pigment. So thank you. This research was supported by ITB and the Synchrotron Thailand Central Lab, and this research was funded by the Ministry of Education of Indonesia and PMDSU Scholarship. Yes, thank you.
So, yeah.
Just a comment. Since you made the link to Namibia, to Tweefontein, and you showed a painting with a beehive.
Yes.
I've just seen a beehive in Namibia in the paintings in the Irongo Mountains just 2 weeks ago.
Yes, thank you. Could you? Yes, this one.
Thank you, great talk. Do you plan to work on maybe model samples to perhaps precise the firing temperature of your pigments? Go back to try to have a precise value of the heating temperature?
Okay. Actually, the heating temperature, when another research already published about the synthetic iron oxide of the hematite, they already obtained the purple pigment in 900 degrees Celsius in the form of the purple pigment, changing from the red one.
Okay, so you have an idea of the
Yeah.
Thank you very much. Very interesting research. I don't have a very technical question, but I'm looking at the handprints in the top right.
This one.
Yeah, so they're made at different moments, but how did they avoid blowing over earlier handprints so that they remain sharp? Do you have any idea about that?
Oh, yes, thank you. You mean the size of the hand?
No, what I mean is that they're obviously not made on the same moment, but I imagine if you blow ochre over it, then you will cover an earlier handprint, and they all seem quite sharp. So I'm just wondering what they used to not blow over an earlier handprint as order to obscure it then.
Yes, thank you for the question. Actually, yeah, maybe it's sometimes like that, but I could answer this question. But some rock art site in Indonesia, so many objects is repainted. So this one maybe one hand prints is made first, and then another hand they made another hand, and they made for another hand, and then I don't know. Maybe it is to archaeology because my background is chemistry. Yeah.
So thank you, Mo.
Yeah, thank you so much.
And we can thank again the speakers.
Yeah.
On the stage. I think you have an announcement.
Just a short announcement for those of you who were not here yesterday morning. So it's now time for lunch. And so if you have not been already at the ESRF restaurant, this is where it is. Again, you can go to ground floor and first floor. You have tablecloths booked tables on the ground floor with coffee, only on the ground floor. So if you want to take a coffee, you can have lunch in the first floor, but take the coffee on the ground floor. And don't forget to have your badge with you, which is the way you will, let's say, pay.